Thank you for the invitation to give a talk in your seminar series. So as you can see from the slide, then I'm from Høgskolen på Vestlandet, and I'm a professor there in computer science and software engineering, and I'm also leading the software engineering research group. And in addition to that, I'm also work package leader for software technology and big data middleware in a research-based innovation center. And this is actually the work that I'll be presenting today is actually coming out of that research center. So I'll be talking about the SmartOcean platform, which is about how you can collect the data using underwater sensor networks in the ocean and how you can provide that as cloud computing services. So it's like from the ocean to the cloud in a sense with respect to data. So this is some work that we are doing in the SFI SmartOcean Center, which is one of these centers for research-based innovation that the Research Council is sponsoring, together with a number of industry partners that we have in the project. And we have just now successfully passed the mid-term evaluation of the center, so we will continue until 2028. So that's very nice. So what is the center about? Well, the primary objective of the center is really to create a wireless observation system for multi-parameter monitoring of underwater environments and installations. So this is things that can collect data, for instance, from fish farms for monitoring purposes. It can collect data from seabed installation, for instance, in the oil and gas industry. It's relevant for collecting data around ocean wind, and nowadays it's actually also relevant for surveillance of vessels and ships that are moving around in the sea, and vessels which should be there and maybe vessels that should not be there, so that you can monitor these things. So the center kind of picks up on the trend that smart systems are becoming pervasive across almost all domains. So we have smart city, we have smart transportation, we have smart energy, we have smart healthcare, and all of these things are of course kind of fueled by these development in Internet of Things, sensor technology, which makes data available and which allows us to build data-driven applications, which in many cases also embeds artificial intelligence. So what this is about is basically to try to improve management, provide monitoring, help in auditing and reporting, give better situational awareness, provide support for making decisions, and also to try to make operations more efficient. So in some sense, it's also about cost effectiveness and building competitive services. So what we are trying to do in the SFI SmartOcean Center is in fact to take some steps to move this smartness also into the ocean domain, where it has not until now been so very present. So why should we do it? Well, there are several reasons for that. First of all, the ocean is of key importance for many things like climate, ecosystems, food and energy production, transportation. And there's also some potential here for economic growth in the next year, according to various reports. So what we are aiming at is in some sense to build enabling technology that can help us to do fact-based ocean management by monitoring sensor systems and providing data services. And in that way also support more sustainable industrial operation and also support ocean research. But to do that, we need data. So what is SmartOcean? You can in some sense think about it as a kind of underwater Internet of Things and cloud computing, but with some new fundamental challenges, which means that we cannot just use existing technology. So here is the bigger picture of what this may look like. So in the ocean, at the sea floor, you have sensor nodes and sensor hubs that are able to communicate by acoustic communication, and you have some form of gateway devices that can bring this to the surface. in such a way that we can then use existing infrastructure to further transmit the data into the cloud, and where we can have data spaces that allows us to share, find, and access data, and also to build or compose data-driven applications. And so the work package that I'm leading on software technology and big data middleware is concerned with the cloud computing part of this. But as you will see in a moment, we also have to somehow think about how the data is collected and the constraints that are there. Because there are some significant challenges with having this concept of underwater IoT. Because first of all, there is limited infrastructure in the ocean. It's not like here where we have Wi-Fi everywhere, and smart city is really not that difficult because you're only 2 meters away from some kind of internet connection. It's also about large geographical areas. It's about the fact that things are not that easy to deploy. It's rather costly, and it's also costly to maintain. Cabling is in general not really feasible. And then there's also the issue of power sources. So for all practical purposes, you have to rely on battery. And furthermore, for the communication, you have to rely on acoustic communication, which has very limited bandwidth. So in some sense, you are back at the good old days with kilobits per second and not gigabits per second. So that also means that there needs to be a tighter integration between what we do in the cloud and how these devices operate. So they typically need to be more smart. You may have to do more of the computing at the edge rather than the cloud. And you also have to think about that you cannot just get all the data that you can collect, but the applications somehow have to tell the sensors what data they need, because you cannot, because of the limited bandwidth, just send everything that you can sense. So these are the key sort of challenges. Now, a lot of the things that we do in the project is related to a pilot demonstrator that we have set up at Østerdal, just south of Bergen, where we have deployed various sensors in this research facility that the Norwegian Institute of Marine Research have there, so Havforskningsinstituttet. So what you see here is a map of the Østerdal area. So we basically have two installations, north and south. And what you see here is the top of one of these installations. And here you see how it's installed. So the top here, there is actually a modem, and then there is a mooring line that goes downwards. And there the different sensors and equipment has been mounted from some of the industry partners. So data from this pilot demonstrator is transmitted from this underwater sensor network that we have here into this cloud platform. So this is kind of the site where maybe we cannot say that we get our hands dirty, but we get our hands wet in this research center. And I have a small video just to give you a little bit better flavor of what it looks like, this site. You can ignore the subtitles, but the point here is just to show you a little bit about what the site looks like. So this is actually the Østerdal station. They also have several cages here that we are using for experiments for monitoring in fish farming. So that's a quite suited infrastructure to try to actually experiment with these things in practice. Here you see the top of that one of these installations where we have this mooring line underneath and where we are measuring the different things. So here are the acoustic modems, and here are some of the sensors that are actually deployed below water and where we are receiving the data. And this is a bit what we can do below water, but here you see this mooring line that was in the picture just before. So this is basically where we test all these different aspects out of to try things out in practice. So in the next two parts of this talk, I will talk a bit more about the SmartOcean cloud platform, the architecture and the services that it has, and also its implementation and deployment. And after that, I will talk a bit about the applications of AI and how that finds its way into the platform in terms of data quality assessment and also sensor battery maintenance. So we'll start with the SmartOcean platform. So this is the public web page of the platform. The platform has very many different elements. I cannot cover everything in this talk, so I will try to just focus on some of the most important elements of that platform. But before I talk about the implementation, in the project we actually spent a year not really coding, but just trying to understand the problem. What was it actually that we were going to solve? So we did a lot of initially empirical software engineering with stakeholder interviews, so that's the industry partners, and also focus groups to basically try to figure out what is it that they are expecting, what are the requirements for such a system in order to kind of properly understand the problem domain that we were in, and also to try to identify what are actually the technical challenges, where are the research problems that we should address. So we actually ended up with almost 1 day of video interviews that were analyzed, and that was then followed up by some focus group meetings for discussion so that we made sure that we consolidated this domain knowledge, the requirements for the platform, and also where are the specific challenges. So the 2 first papers that we published were actually not about solutions, but it was about where are the problems, and try to understand that properly. So then we could move on and start defining the software architecture of the platform, and this is what it looks like. So on one side you have data providers coming from the ocean, and you have data consumers on the other side. And then we have 2 main services. We have a messaging service, which is where the real-time data stream that comes into the system are handled. And we have a data space service where we store historical data. So that's basically time series of the data that are being collected. And then we also have some kind of intermediate services, because we need to deal with data and metadata interoperability. We need to deal with data quality assessment. I will talk a bit about that later. Security and access control is important. Some of the data that one would possibly collect are actually confidential. And we also need to do some data flow service monitoring on the platform to see that everything is actually working properly. So the 2 next papers that we published were actually about solutions. So this were actually 2 papers that presented this software architecture and what the rationale was behind the architecture, why it looked like it did. So just to go a little bit more into detail with the platform and the architecture, this is what it looks like if one opens some of these boxes. So we still have the data providers on one side and the data consumers on the other side. But then for the messaging service, we are using the MQTT industry standard for this publish subscribe based real-time messaging, so that we can pass these messages around in more or less real time. We have also divided the messaging service up to 2 brokers. So there is an ingestion broker where we get the data in, and that's all what we do there. And then we have a core broker where all the processing of the data is actually happening. For the data space service, we have a standard REST API, as most of you will probably be familiar with, to retrieve the historical data. And then internally, we have defined a format based on some international standard for the time series data that is being passed around. Because all the different vendors each have their way of representing the data. So we somehow have to make this more standardized within the platform. And we have defined a data format for that purpose. So the message flow is basically that the data providers have data to send, and they publish that on the messaging service. It's being transformed into the format, and then it's published on topics on the core broker. And here there may be several consumers of that real-time data. So there may be something that needs to forward it into to external data consumers. But we are in fact also forwarding it into the data space service so that we can have the long-term storage. So it can go outside the system, and it will also stay inside the system to actually store the data so that it can later be retrieved. But when retrieving it from the database service, the data is still there. So this is what is meant by the fact that we store it for a long term. So that's kind of the flow in the, or the data flow in the architecture. And then how you instantiate the architecture, of course, depends on the particular case that you have. Here is how we have instantiated it for that Østervold deployment that I showed in the video earlier. So the messaging service, we use something called HiveMQ, which is a software as a service that is provided in the cloud. For the time series database data storage, we use MongoDB, and for that REST API, we have a container on Azure that contains the implementation. And all these different transformers and forwarders internally, they are just running on virtual machines in the cloud. And so in the Østervold deployment, we have Andro that are providing 2 sensors that are publishing data, and also WSense, which is another company in the consortium, also have data. But here we have actually built a bridge between their messaging system and our messaging system, because they were already providing the data via a messaging system. So it basically shows the different ways that you have to accommodate integration in these kinds of systems. And then we have various data consumers. We have more classical dashboards. We have a data explorer that Norse is developing. We have a digital twin of the site. I'll show that in a moment. And also we are transferring data into the Institute of Marine Research. They have this NMDC platform, the Norwegian Marine Data Center, where data is also being mirrored. Just to show some of the data consumption that we have, this is some pictures from a more kind of classical data monitoring dashboard from the Østervold site, where you can see what data is there. And let me see if I click here. I hope I should be able to see. Yeah, so here is the website where you can actually see the data that has been collected. So this is some of the parameters that are being collected: temperature, pressure, oxygen level, and also the input voltage on the device, because that is important to know in terms of when is it that it will soon run out of battery. And if I go here, I can't see it, but it says 11 o'clock, so that's today. So that's the most recent data point. So here we are basically getting data every half an hour. It doesn't really make sense to ask about the temperature every second, because the temperature of the sea doesn't change within seconds. It's more maybe even across days or weeks. So that was one example of an end user data consumer. We have also looked at how we can build digital twins out of this. So these are usually quite data-hungry applications that visualize in a context all data that is being collected. But because of this low bandwidth acoustic communication, we have to do a bit of rethinking about how we do that. So we have looked into how we can build digital twins with much more sparse data. And here is digital twin of the Østervold site. So this is a bit like what you saw earlier in the video with the ship. And then here is actually one of the sensors. And now you can go into the different parts of the sensors, and you can actually see the data that sensor has been collected. So here it's much more contextualized in terms of the deployment. As you can see, unfortunately, there are some fishes outside the fish cage. But I don't know whether they're supposed to be there, whether they have escaped or not. Yeah, so these are the kind of things that one can then build. So that was the SmartOcean platform. And then in the last part of the talk, I wanted to say something about how has AI found its way into this platform as well. And it has that related to data quality and integrity, because if you want to make decision making that is trustworthy, it's not more trustworthy than your data. So it's quite important that we have data which is of high quality and that we can trust. But the challenge is that marine data are quite prone to being bad because you can have biofouling of sensors. You have the issue of batteries, which means that when the voltage of your battery starts to drop, you cannot really trust your sensors anymore. You have waves, current vessels that can tilt your instruments in various ways. And you also have what is called concept drift, where the data distribution changes over time. So for instance, seasonal changes. So if you look at only the winter, then the summer will look abnormal. So you have to take these seasonal changes into account. So you can see here that you can put a nice clean sensor into the water, but when you drag it up again, it looks completely different, and that can really affect what you are measuring. So I have looked into how we can somehow, when the data is coming in, look at the data and somehow tag when there are outliers in the data that we cannot trust. And this is also called anomaly detection here on time series, and we have a PhD student that works on that. But it's basically about identifying data points that are somehow abnormal or deviate according to what the frequent pattern should be. So what we actually did was, again, an empirical study initially to find out what are actually the requirements that industry have for data quality assessment to be useful. And what they came back with was something about accuracy, 85%. Now, accuracy in machine learning can mean different things, but I'll come back to that. Real-time detection was important. So it's like you have to be able to decide whether a data point is abnormal or not in a time which is less than when the next data point arrives. So it has to happen in real time. They also stressed that small data training sets were important, both for supervised or semi-supervised learning, and also that they wanted the data to be labeled. Normally in AI, you would compute like an anomaly score that says how likely is it that this data point is abnormal, but it's difficult to interpret. They want some kind of label saying that this is abnormal or this is not abnormal. So what Tang did, a PhD student working on this, was to actually do an experimental evaluation on 3 data sets from the Østfold site across 36 machine learning algorithms that had been published in literature to see how well they worked according to these requirements. I will not, here are all the results, but I will not go into details, but let's say what were the main findings here. One main finding was to have semi-supervised learning. So for instance, where you only know what the good data points are, clearly outperformed unsupervised learning, also when you only have small training sets. So it is beneficial to train even if you only train on a small amount of data. What is called forecasting seemed to be the most promising approach, but there were some serious limitations when it comes to doing this decision making in real time, and also limitations in terms of the accuracy. So in response to that, we came up with an adapted approach to what already exists. So we took what we learned from that evaluation and came up with a semi-supervised learning algorithm that embedded this forecasting technique, and which also embeds what we call incremental adaptive learning. So instead of being trained initially and not being trained anymore, it continuously trains on the data that it sees in order to gradually learn what is actually normal and what is not normal. And another thing was, in fact, to also encode domain knowledge. So often you know something about what are the valid ranges of a temperature, what is a valid range of a pressure, and you can take that into account as well. And so the results show, when we compare it to the other best performing algorithm, that this adaptive approach does not necessarily compete or is better than all the other algorithms all the time, but on average across many different data sets and measures of accuracy, it actually performs quite well. Actually on the best when we look at it at the complete bigger picture. And also it has actually quite good real-time performance. So on these data sets, this decision-making process were in all cases less than 1 second. So it can quite quickly make decisions about whether a data point is abnormal or not. And that was important in terms of these real-time requirements. So building upon that, because when this was done, it was thinking that we run the anomaly detection in the cloud. But when we now see that we can actually do it reasonably lightweight, we started to think about maybe we can actually embed this data quality control directly on the sensor hubs instead of having to transmit all the data to the cloud and then start the analysis. So together with Andero, we are actually now investigating how we can do this as embedded software directly on the sensor hubs. So this is about making an implementation in C++ of that algorithm that was initially implemented in Python because it was supposed to run on the cloud, so that it can actually run on the embedded processor that Andero have on their sensor hubs. So it's about the data quality assessment, getting in here into the sensor and doing the assessment directly. Because it's much cheaper to compute below water than to transmit. It's much more costly to transmit. And we are now sort of comparing the performance of that implementation to that cloud-oriented Python applications, and the results looks promising. Another area that we have been looking into is software tools for labeling data, because there is really a shortage of labeled data available. A lot of the industry partners and the operators manually tag or label data, but it's quite time-consuming and also error-prone. So what we have been looking into is how could we develop a tool that could aid in this labeling. So it's a kind of co-pilot for data labeling. So the idea is that when some person sits down, a domain expert sits down and labels data in the data set, this tool will automatically find similar patterns in the data and say, maybe this is also abnormal, maybe this is also abnormal, maybe this is also abnormal, so that the labeling process can be a bit more efficient. So this is some work that we are doing together with Reach Subsea to see if we can make more efficient their way of currently manually labeling the data. And then finally, the final application of AI that I will show today has to do with the battery maintenance. So the power consumption is really a main concern when we have deployed sensors underwater that are battery powered. And the thing is that replacing the battery is not like replacing the battery in some device that you have next to it. You have to order a ship that can take you out there, and you have to maybe have divers or other people around that can get the sensors up, replace the battery, put things down again. So it's quite costly, non-trivial, and you have to plan it in advance. So what we have been looking into is whether we could somehow predict when it is that a sensor runs out of battery. So if you look at the input voltage of such a sensor hub, it will typically have this pattern that you see here. You are around 12 volt. And then when it starts to drop, it drops quite quickly, and then after that there is no data. So we have been experimenting with what features do we need to consider to try to predict this. So obviously for the training we need the battery voltage that we will eventually predict, but also battery capacity, time since the battery was deployed. What is the sampling frequency of the sensor, because that consumes power. What is the transmission frequency of the acoustic communication, because that consumes power, and also the environmental temperature is something that we think has an impact, just like the temperature has the impact on the battery of your car. So the red line here shows on some selected data set what we are able to predict out of the segments that we have considered so far. So it looks promising, but I should also say that it should be interpreted with some caution, because we don't have that much variation in our available data sets, so because there has been little variation in the battery capacity or the capacity of the batteries that have been deployed, and there has not been so many changes on sampling frequency and also the transmission frequency. So there is a risk here that there is a bit of overfitting going on, but we will see. So that kind of brings me to the end of this talk. So just a few perspectives on this platform where I have now presented the kind of central services. So the central service is this messaging service, which means that we deal with real-time data, but that we also have a data space which allows us to store the data for long-term uses. And I think a key point is that these two things integrate well together. It's not one or the other, it's rather both. And we have also seen that these AI-based techniques can be very useful embedded in various parts of the platform. In this case for data quality and also for this battery maintenance. And another important thing is that we base the platform on open standards like MQTT, REST, and the data standards, because that makes it all much more adaptable. If you look at the architecture, then it's very easy to scale the different components in the way that it has been put together. And it's also very flexible in terms of how we can deploy the components. We are not locked in, for instance, to one particular cloud provider, but there's a lot of flexibility on how you can instantiate the architecture. So that's it. Thank you for your attention.